All right, let's talk a bit about simplifying square roots. So if I want to simplify square roots, we need to understand what a square root actually is. So I'm going to show a separate example. If I have the square root of 25, we know that this is 5, plus or minus 5, because both of those numbers can be squared to get positive 25. So we know that the answer to this is going to be 5 and negative 5. This one right here messes students up a lot because they forget that negative 5 times negative 5 is positive 25. A negative times a negative is a positive. Most of what we're doing today will be taking the principal square root, which is just a fancy word for the positive version. But again, it's the number 5. And we know this because this is kind of like a question. It is saying that this whole thing with the radical bar stands for a number that you can square to get what's on the inside. All of your your radicals stand for a number that you can raise to whatever this index is right here, which is not written right now, and I'll talk about that in a second, to get what's on the inside. So when I have the cube root actually of 27, I need to find a number that I can raise to the third power. This whole thing stands for a number I can raise to the third power to get positive 27, which if you know, and it's okay if you don't, that is 3, because 3 times 3 times 3, this is 9. And this whole thing is 27. That's the reason why. Now, it's easy when everything's perfect squares, but it's a little bit harder when it's not. Now, again, just as a reminder, whenever this is not written, that it's called the index, this we can tell is a cube root because it has this little 3 index. But whenever it's not written, it's implied to be a 2. So if you ever want to just write a 2 there when it's not written, that works as well. It's just saying this stands for a number I have to raise to the second power to get 25. That's all this whole thing means. There's no magic happening. But what's interesting about this is a lot of students don't know that this right here is the same thing. This square root of 25 is the same thing as saying 25 to the 1/2 power. They mean the exact same thing. So everything that we can do with exponent properties applies to radicals. So all of that stuff about breaking these things up and pulling them out and all that kind of stuff and them canceling powers, that comes from the fact that they're just fractional powers. And I know this might seem a little bit too much, but 25 is 5 squared. So instead of writing 25, I can write that. And just as a reminder of your exponent properties, when you raise a power to a power, you multiply the powers. So this becomes 5 to the 2 times 1/2 is 2 over 2. So it's 5 to the 1 is 5. So that's what's really happening in the background. We never really have to worry about writing it out that way, but every single thing that we do with with radicals, are just exponent properties. Same thing here. I'm going to show you a couple of ways to do this. So this is the cube root of 27. 27 is 3 cubed. You can either write it as a fractional power, like I'm going to do. You can write it as 3 cubed to the 1/3 to get 3 to the 3 over 3. When you do 3 times 1/3, when you raise a power to a power, you multiply the powers. That's 3 to the 1, which is just 3. That's how you can get your answer. I want to point out, you don't have to do it that way. You can also just instead cancel the power this way. Realize that this index always divides your exponent. So this becomes 3 to the, you take this power and you divide it by the index, 3 over 3, because of the fractional exponent thing, which is 3 to the 1, which is 3. You're going to get the same answer regardless of how you do it. But this is mostly helpful when we're dealing with something like this, we have the number 72, and I don't know a number, whoopsie daisies, I don't know a number that I can square to get 2. Remember that this is an invisible little 2 index right here when it's not written. So it's looking, this whole thing stands for a number that I can raise to the second power to get 72. Well, I don't know one of those. No matter what I do, if I'm looking at a number to the, a number squared. So 8 times 8 is 64. Well, that's lower than 72, so it's not that. And then the next integer squared is 9 times 9, which is 81, which is higher. So we know that's not going to be an integer. If it's not an integer, it's hard. So instead of doing that, let's examine the number under the square root. The number 72. Really, this whole process ends up just becoming, how can you break it up? How can you break it up into 2 numbers where one of those numbers is a perfect square and the rest is whatever's left over? So I can do it a lot of different ways. I'm going to show you when it's a small number like this, you might be able to say, all right, well, 36 times 2 is 72. And you can throw that in your calculator just to confirm. 36 times 2 is 72. So I haven't changed anything yet. I've just rewritten the 72 as some factors. Now you can do this even more. You can break it up even more. And there's a way to make sure for large numbers that you can always get the right answer. But that's called prime factorization. We'll talk about that in a second. Now, one property of radicals is that you can break, when you just have multiplication or division, just multiplication or division, you can break it up as individual radicals multiplied of the factors themselves. So you can do that. And we did this. We broke it up into its highest perfect square and then multiplied times whatever's left. Well, you don't want to change that number. 36 times 2 is 72, so we haven't changed anything. If you write just any old number there, you're not going to get the same thing. But the reason we did this is because when we break up that radical, we know the square root of 36. It is 6. And that would be your final answer, 6 square roots of 2. That's how you simplify radicals. Now, some of this, I want to point out, some of this simplifying radicals, most of it, is an artifact from a previous time where we had to use tables, where we didn't have calculators, and we had to use tables of what the values for square root of 2, square root of 3, square root of 5, square root of 7, square root of 11, stuff like that. And we just had to and whenever we did long division or we did anything, we had to refer to the tables. This was to save time. Now, we don't have to do that anymore, but the nice part about this is the fact that it gives us a number sense. Number sense is way more important when we're doing math to save us time and actually understand our numbers so we can choose operations and actually use them in the real world. Even if you can use a calculator, if you don't know the logic behind what you're doing, you should not be doing it ever because you will mess up over and over again. And in real life, this has disastrous results. But let me show you another way to think about it, where instead of writing it like that, we can realize that this is the same thing as 36 times 2 to the 1/2 power. I'm really using this as an excuse to remind you about your exponent properties too. When you have two things, multiple factors, all raised to the same power, you can effectively distribute. I use that in air quotes because it's not really distribution. But then when you start looking at the much higher level ring and field theory and stuff like that, group theory, all that kind of good stuff, you actually realize it kind of is, but whatever. But when you have two things or more that are all just multiplied or divided, not added or subtracted, just multiplied or divided, you effectively distribute your exponent onto both of them and you get 36 to the 1/2 power times 2 to the 1/2 power, which is, going back, which is the same thing as this. And again, that's why I was able to do it. Now, you might be asking yourself, Mr. X, come on. How am I going to know how to break it up? How am I going to know how to break it up? Well, I can take the number 72, and I could do something called prime factorization. If I break these things up into just, re-represent 72 as just a bunch of prime numbers multiplied, then I have all of the individual smallest working parts that cannot be broken up. And then I can just look for pairs. So I like to start, if my number is even, I like to start at the smallest prime number. So I'm going to pull out a 2. Now, what I do right here is I have to figure out what times 2 is 72. Well, that's 36. And you can figure that out by taking this divided by this will give you this. This is a strategy that a lot of students are supposed to learn early on to help them develop the number sense, and I've used prime factorization more than almost any tool that I've ever learned in math. But a lot of students don't really know a lot about factor trees. So I just keep going until all I have on the right are prime numbers. And it's still even, so I'll pull out another 2, and I'm left with an 18. It's still even, so I'm pull out a 2, and I'm left with a 9. 18 divided by 2 is 9. That's how I got that. It's no longer even, so let's try 3. If it's divisible by 3, pull out a 3. And I'm left with a 3. And then I take that, and I put it over there. These are your prime factors. You can throw these into a calculator if you want. These, when all multiplied together, will give you your same original number. Notice 4 times 2 is 8, times 9 is 72. These are all the working parts about it. 2 times 2 is 4, times 2 is 8, times 9. 2 times 3 is 6, times 2 times 3 is 6, is 36, times another 2 is 72. It doesn't matter what order you do these in because multiplication is commutative, so it doesn't really matter. But I do notice that I can also write it as 2 squared right here times 3 squared right here times 2. I did this, even though it seems convoluted, to get you to understand this. It's really more important for big numbers. But this whole thing, no matter what you do, is just the same number. 2 squared is 4, times 3 squared is 9, so that's 36. 4 times 9 is 36, times 2 is 72. Put that in there. So I get 2 squared times 3 squared times 2. And I can break up my radical as 2 squared, 3 squared, 2. And this little invisible 2 right here, index, that when it's not written, it's a 2, it cancels or divides the exponent. So I've got my new power. When I break it out of the radical, when I break this out of the radical, the power is going to get divided by the index. So 2 gets divided by 2. It's invisible right there, but it's still there. There's a little invisible 2 index. 2 divided by 2 is 1, so I don't need to write it. And then right here, same idea. Take the exponent divided by the index, and you get 3 to the 1. And then this one has a lower power. There's a little invisible 1 right there. There's a lower power, so it stays inside. And I get the exact same answer when I simplify. Stuff being multiplied outside of a radical does not jump into the radical to do anything. And stuff being divided doesn't either. Nothing affects what's on the inside of the radical unless it's canceling an exponent of some sort. But at the end of the day, no matter how you end up doing it, you get 6 square roots of 2. Oh, and one last thing. Let's just do a really hard prime factorization just for funsies, because it's a super helpful tool that is very easily ignored. And I honestly think it's one of the reasons that I have gotten so good at math these days and my number sense is high. So let's just take a random number, 1418. If I wanted to find out all of the tiny factors, normally you don't have to do much like this, but if I wanted to figure that out, if I wanted to simplify this and find the square root of that, well, I can do a factor tree. 1418, I can pull out a 2. And I'm left with dividing this thing. I get 709. 2 goes into 14 7 times. 2 goes into 1 0 times. 2 goes into 18 9 times. Well, let's see if this is divisible by. It's not divisible by 2 because it's not even. It's not divisible by 3 because if you add up all the digits, that's not divisible by 3. That's a little special trick that I like to use. If you add up the digits and they're divisible by 3, then the entire original number was. 7 plus 9 is 16. Not good. What happens when we divide it by 7? This one's a little bit harder, and I don't have my calculator ready. I should have come up with a good answer originally. For all I know, 709's prime. That doesn't happen nearly as much as you might think, but let's try a different number. Let's try, maybe I want to do the square root of, so let's see. Not 81, 162. So if I take the number 162, I can pull out a 2, and I'm left with an 81. I can pull out a 3, and I'm left with a 27. I can pull out a 3, and I'm left with a 9, and I can pull out a 3, and I'm left with a 3. Bring that over. Don't forget that. So I can rewrite what's on the inside of this square root in a couple of ways. I could do it as 3 squared times 3 squared. So the first 3 squared came from right here. The next one came from right here, and then 2. Throw it back into a calculator, and you'll see what happens. 3 times 3 is 9, times 3 times 3 is 9. So you get 9 times 9 is 81, times 2 is 162. And then we can break it up like this. The index of this, each one of these has a little invisible 2 index. It divides the exponent when they break out of the radical. So I'm left with 3 to the 1 for this. I'm left with another 3 to the 1 for this. And then this has a power that's too low. So 3 times 3 is 9 square roots of 2. Now there's a lot of different ways to do each one of these. I could have instead of doing it like that, I could have written it like this. I had 4 3s. I could have done like that. I divide when I break it up, and then I want to break this out of the bar, my 3 comes out of the radical bar, and the new power is going to be the old power divided by the index, which is 2. 3 squared is 9, and I get the exact same answer. But again, there's a lot of ways to do each one of these, so just kind of mess with it, and there's a ton of videos online as well, and try to practice it. Khan Academy has some pretty great videos about it.